Let's wait for a couple of minutes, then I will start. Okay, let me start. In this week 7, I will generally discuss the assignment questions uh, for the week 7 assignments, and after that I will discuss about the different types of precipitation and what is the condition of the temperature with height for its formation. Then I will talk about the cloud seeding slightly, then hail formation and different rain measuring devices. And after that, some derivations of curvature effect, solute effect, the Scholar's curve, and the radiation growth by diffusion. Mostly these derivations are done, but still I will do it in a more elaborative way so that people can understand. Okay, let's go to the assignment questions for week 7. I will switch off my video because of the internet connection is okay. First question is, which of the following clouds does not cause precipitation? Just a minute. Which of the clouds does not cause precipitation? The first option is the nimbostratus cloud. As I have already discussed earlier also, that nimbo or nimbus means precipitation bearing clouds. Therefore, this will definitely cause precipitation. Next is altostratus. These are middle level clouds and these are precipitation bearing clouds. And in fact, altocumulus also is a precipitation bearing cloud. Only the high level clouds, which are very small in size, like cirrostratus or cirrus, these clouds generally does not bear any precipitation. Therefore, the only option which is true here is cirrostratus, which does not cause precipitation. Second question is, noctilucent clouds are found in the atmosphere at an approximate altitude of. It is 75 to 80 kilometers. I have already discussed in the previous problem solving session that its height is about 75 to 80 kilometers and it is mostly seen in the middle latitudes, particularly after 60 degrees or so, and it forms at a high height. In hydrostatic balance, the pressure gradient force is equal to, of course, the gravitational force. So the expression becomes dp dz minus 1 by rho, that is equal to g. This is the hydrostatic balance we have discussed so many times, and this is the pressure gradient force in the vertical direction, and this is the force of gravity, the acceleration due to the gravity. Because this is not actually the PG force, it is PG acceleration. So this is gravity, and this is hydrostatic balance. Okay. The next question is, if the lapse rate of an air parcel is less than the lapse rate of environment, the atmosphere is said to be. Given that the lapse rate of air parcel is less than the lapse rate of environment, now what is lapse rate? The temperature decrement with height. Now if I draw a graph here with temperature and this is height, and draw the curves with different colors maybe, this is, see, the lapse rate of the environment is greater, means more decrement of temperature with height. Let us make it like this. This is for the environment, and let's take the green color where the lapse rate of the air parcel, which is less than that of the lapse rate of environment. It means temperature decrement in case of air parcel is less. Therefore, it will be like this. Okay, this is for the parcel and this is for the environment. Just a minute. Yeah, this is for the environment. Okay. Now, you check any height, the temperature of the environment is low as compared to the temperature of the parcel. So if the temperature is of the environment is low, then what will happen? Its density is high, but this parcel's density because of high temperature as compared to environment, will have lower density. So it will get a buoyant force and will move up. It will not come down. It's a situation of an unstable case. Why unstable? Because if we displace it with this parcel from this point, then it will continuously go up. It will not come down because of its buoyancy. Therefore, when this condition is satisfied, that this lapse rate of the air parcel is less than lapse rate of environment, then it is an unstable situation. Now if we go here, the correct answer to the fourth question is unstable. Fifth question is, if the environment is warmer for a rising air parcel, then atmosphere can be considered as similar to that particular thing. Now the opposite thing is given, that is environment is said to be warmer. The environment is said to be warmer. Therefore, this is now for the temperature of the environment. It is warmer as compared to the parcel. Now, if it is cooler, this parcel is cooler, then what will happen? If we displace somewhat, then because of its high density as compared to the environment, it will fall down. And that's why it is a stable case. Remember the concept of stable equilibrium and unstable equilibrium. The same thing. If you have a ball here, you just force it, it will continuously go down, it will never come back. But here, if you force, then it will come back. This is the stable case and this is the unstable case. The unstable is this and stable is this. Simple. Okay. Therefore, the answer to fifth question is stable. Sixth question tells that the Brand-Weissel frequency is the measure of. We have discussed also in the previous session that Brand-Weissel frequency is actually G, gamma of the parcel minus gamma of environment divided by TE. Now, this N, that frequency or the time period, is only for stable oscillations. Why stable oscillations only this N can be calculated? Because actually the frequency is not this N square. Frequency is N. We have to remember this. Okay. Now, what will happen for the unstable case? For the unstable case, this gamma is less than gamma E, as I have already shown in the previous figure also and also in the earlier classes. If gamma is less than gamma E, what will happen to N square? It is less than 0. Therefore, N will come out to be iota, which is not possible in this real world. That's why this frequency or the time period will be always corresponding to the stable oscillation. Therefore, the Brand-Weissel frequency is the measure of stable atmospheric oscillations. Seventh question. In a stable atmosphere, the environmental lapse rate in comparison to the saturated adiabatic lapse rate is, it is less than SALR. Why? It has said that again the stable atmosphere always means that if you look in using this Brand-Weissel frequency only, I have already told, so N square should be greater than 0. Therefore, gamma of the parcel should be greater than the gamma of the environment. Now, gamma of the parcel for saturated parcel, it is the saturated adiabatic lapse rate. This is the saturated adiabatic lapse rate, whereas gamma E is the environmental lapse rate. Therefore, we can easily see that environmental lapse rate is quite less than the SALR for stable atmosphere. Therefore, for stable atmosphere, ELR is always less than SALR. Eighth question, the atmosphere is said to be absolutely unstable if ELR, DLR and SALR, where SALR you know that it is saturated adiabatic lapse rate, whatever it be, environment if it is having a higher is having a higher lapse rate, then parcel will always follow the unstable situation. Just similar to this, just look at this, just look at the Brand-Weissel frequency expression. We already know that for stable atmosphere this should be the condition, and for unstable atmosphere n square should be less than 0. This is for unstable. Now this DALR or SALR is for the parcels, air parcels. Fine. Now for n square to be less than 0, what needs to be done? Gamma E should be greater than gamma. Now this gamma can be DALR for dry adiabatic lapse rate, or it can be for SALR, saturated adiabatic lapse rate. This gamma can be both. Fine. Therefore, ELR should be greater than all other. And why DALR is greater than SALR? This is because DALR itself is always greater than SALR, because DALR's value is 9.76 degrees Celsius per kilometer, and whereas SALR probably is not probably, it is in between 4 to 6, because it depends on both the mixing ratio as well as the temperature. If you have remembered the saturated adiabatic lapse rate expression. The ninth question is, which of the following cause the acid rain? All of the above causes acid rain. I will talk today, but it is there in the presentation of the week 7 lectures by NPTEL. It is present, you can easily have answered it maybe. The 10th question is, the size or diameter of a drizzle, we will discuss today only, is less than 0.5 millimeter. We will come to this. Okay, supersaturation, I have already shown what is the supersaturation. See, relative humidity is suppose 100%. Anything above that is the percentage of supersaturation. Therefore, the supersaturation corresponding to relative humidity 100.6% is only 0.6%. That is the supersaturation. Saturation means relative humidity is 100%. Supersaturation, more than that. The extra as compared to this 100% relative humidity is the actual supersaturation percent. And the last question here is, the value of the saturated adiabatic lapse rate will dash with the decrease in the ambient temperature. So the answer is decrease. Why? What I think is this, if you go with this delta Z double dot is equal G gamma minus gamma E divided by TE delta Z. Let us consider for a particular column of atmosphere, gamma E is constant, which we generally take it as 6.5 degrees Celsius per kilometer. Therefore, this is constant. Delta Z and delta Z double dot, let us consider it to be constant. That the acceleration is same and the displacement is also same. G is also constant. Now, if this ambient temperature means the environmental temperature. So, if this TE decreases, then gamma also has to decrease in order to have this all the things constant. Therefore, gamma should decrease with TE to make all other variables constant. or you can do it with the same n square only. Let us consider for a parcel and environment system, this n square is fixed, then for TE to decrease, then gamma should have to decrease. Therefore, the answer to this question should be decrease. And these are the all 12 questions of the week 7. Now I come to different types of precipitation. This will be helpful in the next week's assignment solving also. Okay. So the types of precipitation particularly mainly considered to be these 4 first, and after that there are many in between.
Sir,
Yes.
सर हमारा जो एग्जाम होगा
Yes.
ये किस टाइप का क्वेश्चन में आ गया मैंने
See, the questions which will be there are mostly these MCQ type questions, what I have given earlier, but I have not done this course. But mostly from the assignment questions, I think that it will be only the MCQ type questions only. And if you have to do some numericals, calculation based questions, you will get the calculator there in that exam center. So you don't need to carry the calculator. This is how
Sir, if we prepare only from assignment question, then it is benefit or not total see the video lecture of this NPTEL course.
See, assignment questions are always helpful, and just see the slides. Whatever the slides are there, you just see those, and if you have any doubt in those slides, you can come to these videos, these problem solving sessions. That will be helpful.
तो एग्जाम में ओनली स्लाइड देख कर जाएगा तो बेनिफिट होगा
Slides will be good enough. You can watch the video for the more conceptual thing, because maybe in the slides many things may be missed. For that you can look for certain things, but the slides are very helpful, what I have seen. Okay.
Okay, sir, thank you.
Okay. Now there are 4 profiles of temperature with 0 degree Celsius isotherm is there. Now first is the for rain. For rain, what is happening? You can see that from the middle atmosphere up to middle atmosphere, the temperature is high, and after that it decreases. This is the particular condition for the rainfall formation. As you can see that some warm moisture should be present in this level. That's why the temperature is large, and after that as it goes with height, it cools down. That is the simple profile for temperature which we expect. The second is the sleet. Now for sleet, what is sleet? You can see that some ice, different shapes of ices are there. In case of sleets, if you see here, sleet is rain freezes before reaching the ground. Okay. Now if rain has to freeze before reaching the ground, then the temperature near the ground should be low, and this is what is represented here. This is the condition for the rain formation, but this rain when comes very near to the ground, the temperature is so low that this region will convert these raindrops to the ice crystals. So that is the sleet formation. Next is snow. Snow formation requires only, you can see that in the mountainous regions only the snow formation takes place, where the temperature goes below 0 degrees Celsius. It is simple. And another is the freezing rain. Freezing rain is what? The rain falls into the ground. After that it freezes. Therefore, very near to the ground temperature is low or below 0 degree. Just near to the ground, the temperature is less than 0 degrees Celsius or below the freezing point. That is the condition for the freezing rain. Therefore, sleet and freezing rain are quite similar, but sleet, the rain freezes before reaching the ground, and here in freezing rain, The rain comes, rain falls, and at that instant it freezes. Now, these different types of precipitations are listed here. So, first one is the rain. Rain we all know. Okay, there is a difference between this precipitation and rain. What is the difference? This precipitation can be all this, but rain is peculiar. Why? Because it only shades the water droplets. So this is only the water droplets, but precipitation consists of both water droplets plus snow and all others, ice crystals. Therefore, I would say that rain, if precipitation is a set, then rain is a subset of precipitation. Okay, snow, we know that we have seen the Bergeron's process for the high latitude region. There the snowfall occurs, we all know. At very large height, when the cloud reaches and the temperature is so low, there is a possibility that there is a snowfall. Another type of precipitation, which is known as the varga, means that is what? A type of precipitation or rain that evaporates before reaching the ground. So there is a ground and the rain is falling, and you can see that suddenly it evaporates. That is your varga. Next is hail. I will discuss in details how these hails are formed. Everyone has seen hail during the thunderstorm events, particularly this time in the this Indo-Gangetic Plain belt and up to West Bengal from in the northern belt, we can find several thunderstorms and hailstorms. So why this occur, we will see. Sleet, as I have already discussed, that rain freezes before reaching the ground. That's why the temperature for that has to be less than this 0 degree Celsius isotherm. Drizzle. I have a mistake here. This is 0.5. Okay, 0.5. Rain with droplets, which is less than size 0.5 millimeter, which is very small. Next is drizzle rain. You can see during the monsoon season, sometimes very small droplet rainfall you can see, that is drizzle. Glaze. Glaze is the freezing rain. Next is grapple. Grapple, this freezing rain, I have already told that this kind of thing, just near the ground, very close to the ground, the temperature is below 0 degrees Celsius. That's why when the rain falls, it freezes immediately. Next is grapple. What is a grapple? It's just rounded snowflakes. Rounded snowflakes which falls into the ground. Some different types. These are different types of this snowfall or precipitation. And then is the ice crystal. Different shapes of ice crystals you can get. Okay, there are many other types of precipitation I have not listed here, but these are the very important types of precipitation. Another important thing is the acid rain. What happens is that when you have gaseous pollutants in your atmosphere, industries are present, there are many factories are present, so those emits this sulfur or nitrogen, and which mixes which reacts with oxygens to give this NO2 or nitrogen dioxide, sulfur dioxide, sulfur trioxide. So these pollutants or these aerosols, when react with the rainfall, they form acid rain, which is very harmful for our skins. So this acid rain is the rain mixed with the gaseous pollutants. This question has come in this particular week only, week 7. Okay, so this is the acid rain. Fine. The next concept which I will talk about is the cloud seeding. So cloud seeding is what? You have moisture. You have enough moisture in the middle troposphere. Now you don't have too many CCNs. What is CCN? This is cloud condensation nuclei. See, for condensation to occur, let me write here. For condensation, saturated vapors are there needed, and the CCNs are needed. The condensation nuclei are needed. Therefore, if you have enough moisture but very low amount of CCN, particularly in the semi-arid regions or somewhere where moisture is typically present but not enough CCNs are present, there what you do is that if you inject certain CCNs from outside, then there will be enough CCNs which will take up this moisture and condensation will take place and droplets will be formed. The cloud droplets will be formed and will enough to shade all the water droplets. This is the process of cloud seeding. Therefore, it is a weather modification technique that improves the cloud's ability to give rain. You don't have enough CCNs initially, but enough moisture is present which can shade to form, which can give huge amount of rainfall, but CCNs are required for condensation to take place. Now, if we inject CCN from the outside, then what will happen? This moisture will be stick to those, or these vapor molecules will stick to those condensation nuclei, and condensation nuclei with a collision process or different processes, they will form huge rain droplets and they will fall out. That is the what you call as the rainfall. Now CCNs are injected into the clouds, as I have already said, and CCN is this cloud condensation nuclei. This I also have mentioned. The first seeding experiment was done using the dry ice, but silver iodide is most commonly used for seeding purpose, but it is a very costly process. So this is an important CCN for cloud seeding. Okay. Next is hail formation, which I was talking about. Okay. Now generally these hail formation takes place in cumulonimbus clouds. Now what are these cumulonimbus clouds? I have discussed already that these are the thunder clouds. Whenever you see the thunderstorms, these are generally related to this. These are related to these thunder clouds. Okay. Now these cumulonimbus clouds are vertically developing clouds. So it's from lower level to top of the troposphere, it is extended. So high is the depth of it. Now, at the very top level, you have some ice crystals. And in between you have some water and ice crystals. So these water droplets are there, as well as ice crystals are there. Now this ice, when it falls, because of its high weight, it falls up to this lower level, but updrafts of the thunderstorm is still there. What is this updraft? The convection. The convection vertical velocity of the air. So this convection will be there, and because of this updraft it cannot fall. As a result, it goes again sticks with different water droplets, and as a result of this hailstone becomes so large. Now when this updraft velocity is somewhat tilted and it is weaker, at that time, means 2-3 times these things happen. So it goes below and it's going up again due to the updrafts. But when these updrafts becomes weak, this falls as a large hailstones. So this is the formation of the hail. So hailstorms occur because of this. So what is happening? At a very larger altitude, you have a ice crystal. Now these ice crystals becomes bigger and bigger because these water droplets from the lower levels, they generally evaporate and condense on this particular ice crystal, and as a result it becomes a big rounded ice. Now this, when falls and when it reaches to the lower level of the cloud, now updrafts tends to rise it up again, and when it rises it up, because of the evaporation of other water droplets, again it condenses. These droplets size grows, but these are still ice. Now these, for 2-3 times or 4-5 times, when it goes like this up and down motion, and the updrafts suddenly then becomes weak, this ice falls as hails. This is the formation of the hailstorms. Next is the rain measuring devices. So what are the rain measuring devices? The first one I am discussing here is the standard rain gauge, which is used in many IMD stations. The next is the tipping bucket, which is a very good instrument to use. And there is a siphoning rain gauge also present. Then is radar based, and then Doppler radar. This is the same essentially. I will discuss each and everything. Okay. So these rain measuring devices, the first is the standard rain gauge. What is the standard rain gauge? You can see that this is the standard rain gauge picture, which is shown here, and it is covered with several barriers, so that it's not easy for the animals to come, or winds particularly does not disturb the rainfall. It is the actual amount of precipitation. This measures the actual amount. It gives the actual amount of rainfall for that particular area. Right? Now in between this, means inside this, there is a measuring cylinder which is present. So when the rain falls over this, it is accumulated here, and there is some graduations which are made in this rain gauge, and we can measure that how much inch or in millimeters of height the water level has reached. The area is also fixed, so we can see the volume of the rainfall, or generally it is measured using the millimeter of rainfall or inch. Okay. Now this diameter of this particular rain gauge opening is fixed. Generally 8-inch diameter is used. And this, how this rainfall is measured? So suppose today is 21st. At 8:30, it has been given that the rainfall for 21st is some 3 millimeter. What does this mean? This means that it is the total accumulated rainfall from 20th 8:30 am to 21st 8:30 am. Therefore the rainfall which is of today is actually the rainfall from today's 8:30 to the previous day's 8:30. So that is how it is measured. And Uh, that is all. Now, in this standard rain gauge, there is another variety which is the siphoning rain gauge, where what happens is that when the rain gauge is completely filled, it automatically releases all the water, and again the rain starts falling. You see, of course, when automatically it refills or automatically it releases all the water, there what happens, there is some error may be possible, because the rain, if it is falling at that time, then that will not be coming in the reading. So some errors might be there. But here also, when you have to use the standard rain gauge, you have to completely release all the water when it is filled up to this level, and again you have to give the empty cylinder, measuring cylinder. This is the first, the standard rain gauge. Next is the tipping bucket rain gauge. What is this tipping bucket rain gauge? You can see that this is the actual figure. You can see a funnel through which the rain falls, and initially it falls to this particular chamber. So this is that where the rain will first fall. Now once it reaches a particular level or amount, which is nothing but generally 1/100th of inch of rainfall, you can convert it into millimeter. When this amount of rainfall is reached, then what happens, it this goes up, this goes down, and the water is released. Okay, now what will happen, now this will get the rainfall, the next rainfall will be got by this. Now when again it is filled, now this will come down, this will go up, and this generally occurs using a reed switch which sounds as a tip sound. That's why it is called as the tipping bucket rain gauge. So the number of tip sounds is telling me the rainfall amount, because each tip corresponds to this amount of rainfall. In this way the rainfall is measured. This is the second. The third is the radar based, where you can see that there is a radar which is radio detection and ranging. Radar's full form is radio detection and ranging. So generally it gives microwave radiation. So it throws out microwave radiation given in these red arrows. Now it reflects from this also. So this microwave radiation is released by radar. This microwave radiation is then reflected from ice crystals, then raindrops or cloud drops, and reflected intensity is captured. Now this ER by EI will give you the rainfall amount. It will also tell us whether hails are present or water droplets are present. So it will give information about everything. So there is a radar equation which tells us many things, like based on the refractive index, you can tell us that whether hails are present or not, and whether rains are present, snowflakes are present. So these things can be easily detected using radar. Another is the Doppler radar, which will also tell us in which direction the cloud is moving. So Doppler radar, based on theory of Doppler shift, now what is this Doppler shift? This Doppler effect is simple. Suppose there is an observer and there is a, suppose this is a source, this is an observer, and so this f of observer is nothing but c plus v of observer divided by c plus vs into fs. Now observer is suppose fixed, therefore this will be 0. Now vs, if it is moving, source is moving towards the observer, then what will happen? The observer's frequency should, the frequency which the observer will get should be high. Now fs is suppose fixed, therefore it will be c upon c minus vs, because vs will be negative, because vs, or write it vs, so vs will be negative. That's why the frequency when source is moving towards observer, so observer frequency increases. This should be the case. So based on the Doppler shift, therefore if suppose there is a cloud and this is the radar, so if it is moving away, then you can see that the frequency will decrease here. If it is moving in the direction of the radar, then you can find that the frequency will increase. This is how the Doppler radar works. This is a simple mechanism based on which it is working. And again, this energy reflected to energy incident, because it has given some energy and reflects some energy, so that gives the rainfall amount. Now, it's not exactly equal, but there is a complete equation, so gives the rainfall amount. Okay. Now comes the three important effects, and based on which you will get the most of the questions of the week 8. So one is the curvature effect, which I will discuss. The derivations I will do, and discussing what are the different, what is the concept behind all those curvature effect, solute effect, and the radiation growth by diffusion, that I will show. Okay. Start. So curvature effect. Now see, one side you have a plane surface of pure water. There is no curvature here. The R is tending to infinity here. This is the radius of curvature. And you have a droplet here. This is a water droplet. But you can see here the curvature is not tending to infinity, but has some value. Some fixed value. Okay, the curvature has some fixed value. Now, if you see this particular molecule over here, this will be attracted by all the other molecules, and there will be many. Therefore, this molecule or this water molecule will not easily get out from these particular bondings. Whereas in this, if there is a water molecule, very less amount of water molecules are present here, which is attracting this particular vapor molecule, the water molecule. Therefore, it will never go out as a vapor. So it will easily go because the bondings are less as compared to this. Therefore, vapor molecules will easily come out. And this force is actually the force of surface tension. So what is happening? In case of a water droplet, the molecule which is present just above the surface, very less attraction. So less surface tension. As a result, vapor molecules comes out. Okay, so we will find that here in case of plane surface of pure water, you have very little amount of vapor molecules, whereas here you have large amount of vapor molecules. Okay, these are all vapor molecules. Now in order to condense this vapor molecule, now in order to condense these vapor molecules, we need more vapors such that saturation such that this the vapor field gets saturated. Okay, that means what? The saturation vapor pressure increases. Okay, the saturation vapor pressure increases. Now if you compare this and this, then what will you get? The time, or I would say the saturation vapor pressure for plane surface will be less than the saturation vapor pressure for curved surface. Why? Because you can see for equilibrium condition to be met here, you need more water vapor molecules. Why? Because this has a very little bindings. The surface tension is very little. As a result, vapor molecules can easily escape. So condensation is also very difficult. Therefore, more number of vapor molecules as you add to this particular air, then only the condensation process will start. That means there are too many vapor molecules. The equilibrium vapor pressure or saturation vapor pressure will be of course very high because there are so many vapor molecules present, but that is not the case here. In case of plane surface, that is not the case. Very small amount of vapor molecules, after sometimes you can see that the condensation process may start, and therefore we can deduce this particular thing, and this is actually nothing but the curvature effect. What is this? Now ES, the saturation vapor pressure for plane surface, is less than the saturation vapor pressure of the curved surface. That is the concept of the curvature effect. Now I will do the derivation, which is also there in the NPTEL slide also. You can see that also. So what is done here is that this is the curvature, and let this be R, the radius, and this is also the same radius, and this is H, the height of the column, and you have vapor here, So of same area, if you take, you have vapor here, E of H, and this is E of infinity, or E of 0, sorry. Okay, but this is the plane surface. This is the plane surface above which you can see the vapor, and this is the curved surface. Simple thing. Okay, so this is liquid and this is vapor. This is also vapor. Fine. Now the area, the volume here will be pi r square h, or you can say that this is smaller. That will be easy to understand. So this will be pi small r square h is the volume. Fine. Now the pressure here should be equal to the pressure here. We know that at a horizontal level, everywhere the pressure should be same. Now we consider that the same pressure will be here and here. Therefore, at this height, the pressure over 1 and 2, if you compare, then what will you get? Or the pressure times area, if you consider, then what will you get? Or the force, if you consider, then what is the force? Is that in column 1 you have the mg, that is rho v into pi r square h, that is density into volume is the mass, that is g into g, and that will be equal to rho L. If this is rho L, this is rho V. Just doing it, pi r square h into g, and you have minus 2 sigma pi r. What is this? The force due to surface tension. Now why this? Because if this is the thing, the tension is acting here, tension is acting here, so the net surface tension force is in this direction, but the mass due to the gravity, the force is here. Okay, therefore there is a negative sign for that. And 2 pi r, because 2 pi r into sigma, because surface tension is nothing but force per unit length. Its unit is newtons per meter. So this is the surface tension. Right? Therefore, we can easily write, I am writing it directly. You can refer to the slides also, that is fine. Rho v, it is there in the NPTEL lecture. So it's pi r square h into g. Fine. So, oh, sorry, there is a pi r will be there. So this pi r and 1 pi and 1 r can go, and you get 2 sigma is equal rho L minus rho v into r h g. So from here we get h as 2 sigma divided by rho L minus rho v into r into g. This is the expression of the height we have got by comparing the forces at the two different regions, and they must be same. This is the concept we have used. And now what we will do is that we will use the hydrostatic equation and find out what is the final expression of the curvature effect. So applying hydrostatic equation, what is this hydrostatic equation tells? I have already written also in the first slide. So dp dz is equal to minus rho g. Now what here is done is from E0 to EH, it is being integrated. What is integrated? Now the dp, or particularly the vapor, the dpv should be equal to minus pv divided by rvt. This is the specific gas constant for the vapors into g. Now if you do it, come in this side, E0 EH dpv by pv is equal minus G, which is common, RV common, and this dz should be there, and yeah, that will be dz, and t is also there, so you can make come out the t can be taken out. So this will be nothing but log of EH divided by E0, and that will be equal to minus GH by TRV. This is what we get. Fine. Now this E0, yes, now this E0 is nothing but the saturation vapor pressure at plane surface of pure water. This E0 is nothing but the saturation vapor pressure at plane surface of pure water. That's why here it is written ES of infinity. That is for plane surface of water. That is R is tending to infinity. Now, what will happen to EH? EH is nothing but the ES of minus R. Why? Because the curvature I have assumed to be like this, so R is in the opposite direction. Actually, the R should be in this direction, the center directing. Therefore, it is taken to be e to the power minus ES of minus R. Therefore, based on these two things, we can write that log of ES of okay, fine, minus R divided by ES of infinity, that will be equal to minus GH by TRV. Now ES of minus R divided by ES of infinity, that will be equal to e to the power minus GH upon RVT. Now, and just put the expression of the H which we have got in this. So what I get is ES of minus R, is equal to ES of infinity e to the power minus 2 sigma divided by RV T rho L. And here there is an assumption that rho L is much greater than rho V. That's why rho V we have not written. And then ES therefore of R, then it will be ES of infinity e to the power minus or plus, because R is already minus R, so 2 sigma upon RV T rho L. So that is the final expression. Okay, this is the Kelvin's equation. I will show how the graph looks like. So this is the Kelvin's equation. But what we are getting from this, we are getting that if my R increases, this R, if increases, then what will happen? This entire thing will decrease. If this decreases, then exponential will decrease, and ES of R, so this ES of R, what will be what? As compared to this ES of infinity, but there is a positive, so exponential is there. So although this thing is decreasing, but this ES of R, this ES of R will increase as compared to ES of infinity, and that is what we call as the supersaturation. Okay, with respect to plane surface of pure water, the saturation vapor pressure for a curved surface will always be high. Why? Because exponential of this term. Now as R tends to infinity, you can see this term is 1 because e to the power 0 is 1. Therefore, ES of R will be equal to ES of infinity, which is true. That is plane surface of pure water. Simple. So more the R is decreasing, more the R decreases. So as this is nothing but as R decreases, means more curvature. So more curvature as the R decreases, this ES of R will increase as compared to S of infinity. This is the entire thing about curvature effect. Fine. The next thing is the solute effect. But before knowing the solute effect, I will talk something about the cloud condensation nuclei only, and then discuss what is the solute effect, and then formulate the expression for the solute effect, and then we will go for the radial growth due to diffusion. Fine. So this CCN, the cloud condensation nuclei, are of three types based on the sizes. One is the Aitken. This is the type of a nuclei, then large, and then giant. Now, what is the size of each? Just it is mentioned, so it will be helpful. R will be less than 0.2 micrometer. This will be 0.2 to R to 1 micrometer, and this will be R greater than 1 micrometer. Fine. Now, generally this CCN size is about 0.2 micrometer to 2 micrometer. And cloud droplets, as I have already mentioned, cloud droplets have size about 100 to 1000, sorry, 100 to 1000 micrometer. And rain droplets is about 1000 micrometer to 5000 micrometer. Fine. So mostly this is from 10 to 100 micrometer. Okay. So this will be helpful in solving one of the questions of the assignment. Okay. Next comes to the solute effect. Now we have seen the effect of the curvature of the droplets. So if the R decreases, more is the curvature, more will be the saturation vapor pressure, because vapors are easily getting out because the surface tension force is less, the binding force is less. And because of which what happens? Condensation will not easily taking place. So for that more vapor is required. So saturation vapor pressure increases as compared to plane surface of water. But in case of solute effect, what is happening? Solute means some nuclei or condensation nuclei or salts. It can be salts, different salts, these solutes. So what is done is that if in that droplet now some salts are also added, solutes are added, then what will happen? These solutes generally blocks or occupy the sides of the surface, and some solutes like salts, they form strong bonds with water. As a result of both these things, it is difficult to knock out any water molecule. So what happens when solutes are more? Evaporation is less, and the saturation vapor pressure in case of solute will be less than the saturation vapor pressure at plane surface of pure water. Here plane surface or curvature is not a big deal, but pure water is the important thing, because here we are talking about the purity, whether some solutes are present or the solutes are not present. So if the solutes are not present, the ES is more as compared to when the solutes are present. Why? Because evaporation is more, vapor molecules are more, so saturation vapor pressure will be more in case of this. But here when the solute is there, evaporation is less, so the saturation vapor pressure will also be less. And condensation will start even before the saturation. And the same thing occurs in hygroscopic nuclei. And these hygroscopic nuclei are nothing but salts or sea salts. These binds well. Okay, so this is the concept of the solute effect. Now I will derive. It's very simple. It is there also, you can refer to that, but I have given the concept for this particular thing. You will get several questions from this this particular section in the assignment. Okay, so in this case we have to remember that the condensation will start early. Now suppose the derivation starts with this, say E dash is the new saturation vapor pressure with solutes. Therefore E dash, this is applying Raoult's law. Which is a law in the physical chemistry. So E dash is equal to the mole fraction of the water into ES. When this is the solute is present, when solute is not present, and this is a chi W. Means the amount of dilution, you can say. Now therefore E dash is the mole fraction. So NW divided by NW plus NS. N is the concentration of the solute. Fine. Now for dilute solution, NS of course will be less than NW because solute particles are less. Therefore chi W, this is for the simplicity of the expression we are writing this. So NW, I take out NW again, so it is 1 plus NS by NW, right? Now this will be NW, NW will cancel, so it will be 1 plus NS by NW minus 1. What does this give? NS by NW. Simple. Right? Now this N of W is nothing but the given mass of the water by that is the molar mass. Simple. And the NS will depend on the degree of ionization into MS divided by MS. This is the same, given mass by molar mass of the solute, but this is the degree of ionization. Fine. Therefore chi W will be what? 1 minus NS by NW. So this will be I MS by capital MS into MW by, this is what it is. Now MW will be written as 4/3 pi r cube, because this is the volume of that particular thing, water, and this is the rho liquid is, as we have already considered in the curvature effect, that rho will be the density. Fine. So what we can write is chi W therefore will be 1 minus I MS by capital MS into 3 by 4 MW divided by pi r cube rho L. So chi W can be written as 1 minus B by r cube. And what is this chi W? E dash by ES. Right? Now therefore this is the solute effect expression. And that solute effect, you can see, is depending on R, 1 by r cube. Therefore they have combined both curvature plus solute effect you can see you can refer the slides. I'm just writing it directly. So it will be Es of R by Es of infinity will be actually equal to 1 plus A by R minus B by R cube. This is nothing but the Kohl's curve that I will show in the next slide. So how this 1 plus A by R is coming? So you remember that Es of R by Es of infinity, only when curvature effect is considered, is actually some exponential of A by R, right? Some A is all those constants, and this can be written as 1 plus A by R, and we are neglecting the higher order terms, so only this. So this 1 plus A by R, and you are multiplying with 1 minus B by R cube, which we have got from the solute effect, and we are getting this. This is the expression. Fine. And this is the curve corresponding to this Kohl's curve, and we can see that this is the supersaturation, means this is actually your Es for plane surface, that is the vapor pressure corresponding to the plane surface, that is taken as the reference 0. So what is happening is that you see the Kelvin term as the R, this is the R, okay. So as the R is tending to infinity, you can see that this Kelvin's curve, this dashed curve, this is tending to 0, that is tending to Es at infinity, okay. And this is all our Es of R. Now due to solute effect, you can see that this is the curve which are following. It never goes above saturation vapor pressure of plane surface of pure water. It will never go. Why? Because these sea salts or the hygroscopic nuclei which are present, which acts as a solute, they do not allow this particular what you call as the droplet to convert it into the vapor phase. So less evaporation and less number of droplets near the surface. So this is the curve which is expected, that is 1 minus B by R cube, okay. And this is the term which is 1 plus A by R, which is the curvature effect. So this is the curvature effect, where you have more vapor molecules as compared to the plane surface of pure water. And the net curve looks like this, and this black curve is actually 1 plus A by R minus B by R cube, the solute effect term and the Kelvin. So this is all about the Kohl's curve, which consists of both the curvature effect as well as the solute effect. Now is the big derivation of the radial growth of the droplet by diffusion. So the derivation is already there in the NPTEL slides or the lectures which are there, but I am doing it because there are some places where there will be maybe some gap, so I can fill up that gap using this particular derivation, and this is the last thing I will do. But since it's a big derivation, so it may take 20 to 30 minutes to understand fully. Okay, so this is the radial growth by diffusion. Now for that, they have used the Clausius-Clapeyron equation, which we know that the saturation vapor pressure at any temperature can be related to this temperature. So suppose we have some saturation vapor pressure. The actual thing is that you have a droplet and you have a vapor field. Okay, so from center it has some r and it is going to infinity. Just consider that it is going to infinity like that. Okay, now r can go to infinity, tending to infinity. Okay. Now let us consider that EVS is the saturation vapor pressure. Now rho is the density. Now Clausius-Clapeyron equation which we have derived also, that is dES by dt, is the actual equation, is L divided by T and alpha V of S minus alpha L. Alpha of the saturated vapor and alpha of liquid. Fine. So what we can write here is that dES dt, just some simplifications which needs to be done, and that will be equal to L upon T of 1 by rho by Vs minus 1 by rho L. Why we can write it? Because alpha Vs is nothing but 1 by rho Vs. Similarly, alpha L is 1 by rho L, because there is a definition. Alpha is 1 by rho, the density. Fine. That is, we can further write it as L upon T and just simplify this term. So rho L minus rho Vs divided by rho L rho Vs. That's all. Fine. Now this rho Vs is much smaller than rho L, because the specific volume of vapors, as we know that if you see the gases, the molecules are so far apart and it occupies a larger volume. Therefore, the specific volume of these vapors will be large as compared to the liquid. That's why the rho Vs is small as compared to rho L. Therefore, what we can write from here, dES by dt will be equal to L rho Vs divided by T. Fine, because rho L, okay, if you just L by T, now rho and rho Vs will come at the upper side. So let me write it. It will be easy to understanding. Rho Vs divided by T, and here we are assuming that rho Vs is much smaller. So rho L. So rho L chops out and we get this. Fine. So this is the first equation which we have got. Fine. Now the saturation vapor pressure will be equal to rho Vs RV into T according to the ideal gas equation. Now dES dt will be equal to d rho Vs by dt. Just I am differentiating into RV into T. See, when we are differentiating with temperature, rho is a function of temperature and T is of course there, but RV is a constant. So don't differentiate that. Therefore, it will be rho Vs into RV, and T differentiation is gone. Okay, now this will be now 2. Now you combine these two particular thing, and what we will get is, I am writing it here, so L rho Vs by T will be equal to d rho Vs by dt into RV into T plus rho Vs into RV. Simple, just we are combining those things, or just writing the right hand side of the first equation here. Okay. Now, whatever the expression we get, let us divide it with rho vs rv into t. So let's do it in the next slide. On doing that, what we get is L divided by rv t square, because you have divided from here, rho vs cancels out, so rv t square will left out. That will be equal to d rho vs by dt 1 by rho vs, there is an rvt, there is an rvt monitor, sorry, will out, plus rho vs divided by rho vs rvt, and there is an rv. So rho vs rv is out. So what we are getting is d rho vs by dt 1 by rho vs plus 1 by t. This is the expression which we are getting. Now further, if we can simplify, so we can write 1 by rho vs d rho vs by dt will be equal to L by rv dt by t square minus dt by t. Just reshuffling the terms. Now what we will do is that we will integrate this equation, say 3. So integrating third equation from temperature at the surface, that is Tr, to temperature of the environment. So this is the environment and Tr is the surface. Fine. Now if we do it, then let us write, so from Te to Tr, I'm sorry, this will be from Te to Tr. Okay, we are integrating from environment to the surface where the vapors are present. So it will be T rho Vs by rho Vs, that will be L by Rv, then Te to Tr dt by t square minus Te to Tr and dt by t. Simple, just integrating it. So what we will get is log of rho Vs at Te to Tr will be equal to L by Rv, and this will be minus 1 by t. So it will be minus 1 by t, Te to T, sorry, Te to Tr minus log t again, Te to Tr. So step by step we are proceeding. Okay. Now let us consider that rho of Tr is equal to rho Rs, let us be rho Vs, and rho Vs of Te will be equal to rho Es. Just writing that. So log of the saturated vapor density at the surface of the droplet, and this is the saturation vapor density at the environment, that will be equal to L by Rv, it will be 1 by Te minus 1 by Tr, because there is a minus sign, therefore they have shifted, log of Tr by T. Simple. Now as Z tending to 0, we know that log of 1 plus Z is Z. This is a mathematical thing. So log of y by x, it is very well shown that it will be written as log of 1 plus y minus x upon x, and that can be further write it as y minus x upon x. If this is small, then only we can write it, of course, because then this will be valid. Fine. Now here what we will do is that we will assume that this tr minus te, of course there will be not much difference, so tr minus te divided by te is small. Let. So if this is small, then what will happen? Just use this expression. So it will be rho rs minus rho es divided by rho es, L by rv 1 by te minus 1 by tr, and minus, see this log tr by te is there, just we are writing that as, see log y by x is written as this, so it will be written as what? Log of, or not log of, just tr minus te by te. Okay, that's all. Fine. Now again, if I write properly, then what will happen is rho rs, only the log terms I have changed it like this, so minus rho es, okay, divided by rho es will be equal to L by rp tr minus te divided by tetr, just simplifying it, this is a mathematics only, so tr minus te divided by te. Fine. Now the left hand side, let it be like that, rho es divided by rho es, that will be equal to tr minus te by te. I am taking out this particular term, so what I will get is L by rv, and tr minus te by te is gone, so it will be tr minus 1. This is the expression which we are getting, let this be 4. So this is the expression which we are getting, that is the saturation vapor pressure or vapor density at the surface of the droplet minus the saturation vapor density at the environment, and to that of that the saturation vapor density at the environment will be equal to the temperature which is at the surface of the droplet, temperature at the environment divided by the temperature at the environment, and it also depends on the latent heating and this L and the specific gas constant and the temperature of the surface. Okay, now we will start talking about the diffusion. Okay, so what is happening is that, so diffusion of heat is given by like this, so this is the diffusion of heat away from the droplet. So it will go from the surface to the vapor field. So that can be written as dq dt, that will be equal to 4 pi r into k tr minus te, right? Because whatever the temperature difference is, suppose this is the droplet, here the temperature is tr and here it is te, so whatever the difference in between that will release the heat from the surface to the ambient vapor field, where r is the radius of curvature of the droplet and k is the coefficient of thermal conductivity. But this is the conductivity kind of equation, conduction equation. thermal conductivity. Now will come the diffusion. So, okay, fine. Now this dq dt can be written as the mass times the L, the latent heat, or let me write it, L I have written like this. So L dm dt can be written as this. Same thing. The amount of latent heat which is there, that will go to the vapor field, because saturated vapor is there. If some saturated vapor condenses and the droplet becomes bigger, then what will happen? Latent heat will be released, and this latent heat will also go. So the latent heat as well as the and the conduction will take place. Fine. So that is what I was saying, that as droplet grows due to conduction, condensation, not conduction, condensation, latent heat will be released, and that will be transferred. Okay. Fine. Now comes the actual diffusion equation case. So suppose this thing is not very properly written in that slides, so I'm just explaining it in between. It will be known to you. The droplet has radius r, which we are considering here, droplet of radius r, okay, and it is located in the vapor field. What we are assuming so far, with concentration of vapor molecules at distance. Now I am not writing smaller, but I am writing capital R. Okay, this smaller can be replaced with capital R, just small change. Okay, this smaller is nothing but capital R. Okay, from the center of droplet. Okay, so at surface, this vapor density of at R, that is at the surface, that is N into m naught. M naught is mass of one vapor molecule. Fine, and N is the number. Perfect. Now the diffusion equation is delta N delta T, where N is again the concentration, the number is the diffusion coefficient, grad square N. This is the molecular diffusion coefficient. Molecular diffusion coefficient. Fine. Now at steady state, what happens at steady state? This partial derivative with time will be 0. Delta N means equilibrium state, this should be 0. So d grad square N should be equal to 0. So you just see, this is the Laplace equation, right? Now this Laplacian can be written as 1 by r square delta delta r, r square delta N delta r. This should be equal to 0. And we get N of R will be equal to C1 minus C2 by R. Now some conditions. Of course, without that condition we cannot get anything. So R, if tending to infinity, if that curvature is tending to infinity, or the radius or radial distance, I would say. So if radial distance is tending to infinity, then n will tend to n of infinity, that is the ambient vapor concentration. Of course, because the radius is very large from the droplet, so it's not the droplet, it's over the ambient field. Now as r tends to r, n will be tending to nr, or small r you can write. But small r and capital R are same, I have already told. So this is the vapor concentration at surface of droplet. This is important, this is not shown, so this is an extra thing which will help to understand this particular derivation. So n of r will be equal to n of infinity, therefore, minus r by capital R, n infinity minus nr. Right? Okay. Because we have started with that radius is having smaller and the radial distance is r. Okay. Now just a minute. The annotations. To add one slide. It's added. Now I can go. Yeah. So this is the equation which we have got. Fine. Now, the flux of vapor molecules onto the surface of droplet will be what? See, this dm dt, the change in the mass, will be equal to 4 pi r square d into delta n by delta r at r is equal to smaller into m naught. Because this is the change in the means the concentration of the vapor molecules with the radial distance at the surface into m naught will give the total amount of vapor molecules times the surface area of the droplet and into the diffusion coefficient. That becomes the dm dt. Fine. Now, therefore, what we are getting, see, if you calculate this, that delta n by delta r at smaller, this comes out to be 1 by r n infinity minus nr. If you put it in this, then we get dm dt will be equal to 4 pi r square d n infinity minus nr into m naught and divided by r. So r cancels. Therefore, what we are getting is dm dt will be equal to 4 pi rd n infinity minus nr into m naught. And what is that? What is n infinity into m naught? We have written earlier, that is the density, 4 pi rd rho v minus rho v r. This r is representing the surface vapor density. Fine. So this is what we are getting, and we know that this dm dt is, we have already got another expression of dm dt. So finally, what we can write is that this. So the expressions which we have already got is Tr minus Te is nothing but L by 4 pi Kr dm dt. Right? From where we have got this expression? This is the, this, from this we are getting, because L dm dt we have written, and R is in general any distance L. the radial distance. So we can write this. This is the first thing which we have got. Second thing what we have got is that density expression, that is rho saturation density at the R, means the surface, rho ES divided by rho ES. The first expression which we have got, LD by KTE rho V minus rho VR. Now from where we are writing, I am coming L by T R RV minus 1. See this expression, this one, the fourth equation. In this fourth equation, this TR minus TE is replaced. See, TR minus TE is replaced, and this dm dt is nothing but this. So this thing has been put here, and then only we have got this expression. Fine. Now we can also write in another way. So this is rho RS minus rho ES divided by rho ES. That will be equal to LD upon 4 pi RK, or you can write small r, whatever you want, okay, TE D into dm dt. Just writing this thing, okay, and you have L by TR RV minus 1, right? Now this DD cancels out. So we get one expression, this. Another expression is that rho V minus rho VR is actually 1 by 4 pi RD rho ES. Fine. This is the another expression which we are getting. Now further we can write, if we give a rho ES. See, this rho V minus rho VR is this one. So 1 by 4 pi RD dm dt. So 1 by 4 pi RD into dm dt. And divided by rho ES will give this. So this is the first expression, this is the second expression. And we all have this dm dt. And what is m? Is nothing but 4/3 pi r cube into rho L. So dm dt will be how much? It will be 3 into 4 by 3. So 3 cancels out, pi r square rho L dr dt. Fine. So this dm dt therefore can be written as, but before that another thing is there, that rho V minus rho VR by rho ES plus, if we do it in this way, minus rho ES divided by rho ES. That is what I am doing. This expression A and B I am adding. So A plus B. If we do this, then we get is as rho V minus rho VR plus rho RS minus rho ES divided by rho ES. Now if rho VR is equal to rho RS, then this chops out. What I get is rho V minus rho ES divided by rho ES, and that is nothing but rho V by rho ES minus 1, and that is super saturation. S is the actual saturation, minus 1 is the, so S minus 1 is the super saturation. Fine. And then we can write, see, rho V minus rho ES upon rho ES is nothing but the summation of these two. So from here we can add A plus B and write down as S minus 1 will be equal to 1 pi 4 pi R rho ESD into dm dt plus L by TR RV minus 1 L divided by 4 pi R K TE dm dt. Now just we will write the dm dt expression in the next slide, but for that again I have to add a slide. Just a minute. Okay, now I add a new slide and this will be the last, I think. Yeah, now dm dt is therefore what? Now it will be 4 pi r, which I have taken from the denominator, or I have taken it from this the above expression. So you just try it, you can get it easily, or you refer to that notes which is given in the NPTEL slides. Watch the video, that will be easy. And this becomes L by KTE plus 1 by d rho es. Fine. And dm by dt I have already found out that it is 4 pi r square dr by dt. That is 4 pi r s minus 1, supersaturation minus 1 is AC supersaturation, more than 100% humidity. And in the denominator we have L by R V TR minus 1, and you have L by KTE plus 1 by d rho es. Fine. Now 4 pi r, 1 r will be there. Therefore r dr dt will be equal to s minus 1 divided by same expression, just divided by rho L. L by k rho L T and plus 1 by d rho L rho es. Fine. And this rho es can be further written as EES divided by rho your RV into TE. This can be written. So what we are getting is R dr dt, the diffusion growth rate. What we need to remember from this, not this entire derivation, but this derivation is to make the everything clear, is s minus 1 divided by fk plus fd. Okay, so fk is the thermodynamic term. Fk is the thermodynamic term and Fd is the vapor diffusion term. So these two terms and the super saturation, these are actually responsible for the diffusion growth rate. Fine. And whatever this rho Vr, these things we are using, see, this also consists of this E dash R by RVTR, because this is the ideal gas equation, and this rho Vr is therefore can be written as Es of infinity of 1 plus A by R minus B by R cube, and you divide by RV by RVTR. So what is happening here? Here both the solute and curvature effect are there. So when we are using rho Vr, these two things are there. So it's a very large derivation, of course, and it took a lot of time. Just try it, understand it. This will be much more clear. The steps are much more clear. So you try it. I will give this this particular slides, and the recordings will be shared soon. So I will end here this particular lecture. We have seen the assignment questions, and after that types of precipitation, cloud seeding, hail formation, then different rain measuring instruments, and talked about the curvature effect, solute effect, the Kohlhertz curve, and radiation growth due to diffusion, which is a very big derivation, but slightly I have tried to elaborate it to understand each and every step and what is the meaning of that. Okay, so I will stop here and thank you. Goodbye.